if I take the derivative of x, I'm going to get 1. And here, I've got that exponent of 2/3. That's going to come down. I'm going to write this, I'm going to write out an extra step here and actually write this as 3 times the 2/3 times x. And then I'm going to subtract 1 from that exponent. Because it's a fraction, subtracting 2/3, subtracting 1 from 2/3 is going to give me negative 1/3. And now my 3's can cancel out. So really my question here is, at what values of x is the derivative equal to 0? So kind of an extension of doing something with that derivative. There are a couple of different ways that we can write this. I'm going to take a minute to rewrite this to say, well, my 3's canceled out. So I'm looking at 1 minus, and then because this x is raised to a negative exponent, it's a choice, but I'm going to choose to write that as 2 over x to the 1/3. Do you guys like fraction exponents or radicals? Okay, so a 1/3 means it's a cube root of x. Don't have to rewrite it that way. I think it's a little friendlier to look at that way. So if it's a 1/3 exponent on the bottom, then it's a cube root. Yeah. And I'm going to set this equal to 0. And now we get to solve this thing. So if I were looking at this personally, I would probably move this to the other side and cube both sides to get rid of the radical. You could also look at that and say, hey, we've got fractions. Let's multiply the whole thing by the denominator to eliminate the denominator. Either one is fine, but I'm going to do this. I'm going to write that as 1 is equal to 2 over the cube root of x, and then cube both sides. And 2 cubed, 2 times 2 times 2 is going to give me 8. And when I cube the cube root of x, I'm just left with x. So I know that the value here is going to be 8. And that's my only x value where the derivative is equal to 0. In terms of my handout, the next question that I asked is the function defined at x equals 8? So this is kind of going back to stuff from midterm 1, but thinking about the domain of the function because it's going to come up again for us real soon. This function, the domain is all real numbers. Cube roots, totally fine to plug negative numbers into. And the original function is not undefined anywhere. Is there anywhere that the derivative is undefined? Like any values of x that you couldn't plug into the derivative? I'm going to go with 0. Because my derivative has an x in the denominator. So my derivative is not defined at 0, but the function itself is, so we're good. Now I know that not everybody has talked about this yet, but some of the sections have gotten to talking about increasing and decreasing functions. And all that means is the derivative positive or is it negative? So if I look at, for x equals 8 here, that's the only place where my derivative is actually equal to 0. So I kind of like to think about this as a number line for my derivative, and 8 is the dividing point where my f prime of 8 is equal to 0. And I'm looking on either side of that point to figure out whether my derivative was positive or negative on either side. So this is, again, kind of going back to that pre-calc skill. If I'm trying to solve an inequality, I can put the values that make it 0 and then choose some test points to figure out whether I was positive or negative on either side. Since I'm going to be plugging things into this derivative, I know that 0 is a problem because 0 is a place where my derivative is undefined. So I want to make sure to put that on my number line too. F prime of 0 does not exist. So if I need to pick a number bigger than 8 to plug in, and I'm not using a calculator, what's a number that we can take the cube root of other than 8? Sure. So let's try 27. So if I plug in 27, the cube root of 27 is 3. So if my test point over here was 27, then f prime of 27 would look like 1 minus 2 over, when I plug in the 27, that's 1 minus 2/3. Is that a positive number or a negative number? It is positive because 2/3 is less than 1. So I know that my derivative is positive over here. And since my derivative is telling me about the slope of the graph, if my derivative is positive, it means that as I go from left to right, my graph is going up. I'm going to pick a number for us between 0 and 8. I'm going to pick 1. So if I pick a test point in here of 1, and I look at f prime of 1, that's going to be 1 minus, the cube root of 1 is 1. That's why I chose it. So I'm going to have 1 minus 2 over 1. And that is definitely a negative number. Thinking about what that means graphically, as I move from left to right, that tells me that my graph is going down. If I pick another test point on the other side of 0, and again, I've included the 0 because it's a place where my function is where my derivative is undefined. So if I pick a test point over here, I'm going to go ahead and pick -1. And if I look at, I did not leave myself a ton of room here, but if I look at f prime of -1, that's 1 minus 2 over the cube root of -1 is -1. So that's the same as releasing 1 plus 2, which means I am positive. So my graph was going up. So when we talk about the phrase relative extrema or local extrema, I like to think about this in terms of like roller coasterology. So if I were on a roller coaster and this is kind of the path of the roller coaster, if I was going up and then I started to come back down, then I must have been at a maximum value. And if I was going down and I started to go back up, I must have been at a minimum value. When we talk about a relative extrema or a local extrema, we just mean that if I just look right around this point, I was kind of at the top of the curve. And if I look right around this point, I was at the bottom of the curve. So in terms of, I didn't actually answer my question, which was intervals where we are increasing and decreasing. So our function is increasing on the intervals from -∞ to 0 and 8 to +∞. And my function is decreasing on 0 to 8. And then in terms of thinking about relative extrema, I know that I have a relative max at x equals 0. And I have a relative min at x equals 8. Just for fun, I'm going to graph this thing. So we've got y equals x minus 3x to the 2/3. And we zoom out a little bit here. You can see that that matches what we have. So 0 is a relative maximum. And at x equals 8, we're down here at a relative minimum. And we asked the question about an absolute maximum or minimum, it really means we're taking a step back and I'm like looking at the whole picture and saying, what's the highest or lowest point we ever get to on this graph? Now, if I'm really looking at the entire picture here, then there is no lowest point because this just keeps going down to negative infinity forever. And if I was looking at the entire picture, this keeps going up forever. But sometimes, especially in biology or when we're talking about word problems, there might be physical constraints on what's happening. And if there are physical constraints, then I want to know, based on those physical constraints, what's my maximum or minimum? So the next question on my handout says, if we only care about the part between -1 and 27, what is the highest and lowest point on the graph? So we can think about it graphically, but I want us to have tools to do it when Desmos is not around. Like on your quizzes and exams when Desmos is not around, right? We've got to have some tools to do this mechanically. So the way that we're going to look for absolute max and min is to find those relative extrema, look for those places where we had relative extrema, and then also check the endpoints of the interval. So to find absolute max and min, we're going to check, in our case, we need to check at x equals 0 and at x equals 8. And then we also need to check at the endpoints that I gave us, which were -1 and 27. And I just realized that if anyone joined after I put these links in the chat, just going to toss them in the chat one more time. And when I say to check these, what we're looking for is the highest and lowest point on the graph. And to figure out how high we are in the graph, we're looking for the y values. So when x equals 0, I'm looking at f of 0, not the derivative, just the actual function. 0 minus 3 times 0 to the 2/3. Well, that's 0. Cool. 8, f of 8 looks like 8 minus 3 times, I'm going to do math in my head here. So my function, just to rewrite it so it's back on the page for us, or back in view. When I plug in 8 here, I'm going to take the cube root of 8. So I'll be at 2. And then when I square it, I've got 4. 3 times 4 is 12. So I get a value of -4. F of -1, -1 minus 3 times -1 to the 2/3. Well, the cube root of -1 is -1, but when I square -1, it becomes positive. So this is -1 minus 3, and I also get -4. And when we plug in 27, f of 27, it's 27 minus 3 times 27 to the 2/3. The cube root of 27 is 3. When I square it, I get 9. When I multiply that by 3, I'm back to 27. 27 minus 27 is, in fact, 0. When we're talking about the absolute maximum and minimum, we're looking for the y values. So now I'm just looking at this list of y values, and the minimum value is 0, and the maximum value is 4. No, not 0. I got those backwards. Good times. I missed minus signs in there, folks. Which is bigger, 0 or -4? 0. I did the same thing. I just made the same mistake. So our maximum value is 0 and the minimum value is -4. For those of you that are starting to see these in web work, homework, just be careful because sometimes the question is asking you the x value where the maximum or minimum point is. Sometimes it's asking you for the point, meaning like x comma y, and sometimes it's just asking you literally for the y value. So just be careful if you're seeing those in web work. Should we take a derivative? Are you all done? We got a derivative. Okay, so I'm gonna like speed run this, not really. Derivative of x cubed, I'm gonna end up with 3x squared, and then I'll leave the x minus 4 in parentheses. I'm gonna add to that x cubed, and then when I take the derivative of x minus 4, I just get 1. And someone in the chat asked you have to write the 1. Heck no, you do not have to write the 1. Everybody's gonna know you took a product rule already. Now, there's another question in the chat about when do you need a sign chart. I only need the sign chart if I'm looking for relative maximum. If we're looking on a fixed interval, I just have to figure out where is the derivative equal to 0 and to check those places and the endpoints. It is good to practice setting this thing equal to 0 and solving for x. By the way, if my derivative is equal to 0, just thinking about that geometric meaning of derivatives, if my derivative is equal to 0, I know that's a place on the graph where I have a horizontal tangent line, because that's a place where my slope is 0. Okay. I would factor an x squared out of this because I've got 2 pieces. And if I pull an x squared out of the whole thing, then from the front, I'm still left with that 3 and the x minus 4. And from my back piece, I'm just left with an x. And if I clean that up a little bit, inside of the parentheses, I've got a 3x and another x. So that's 4x. And then, did I do that right? And 3 times -4 should be minus 12. I think I got that right. Which means that if we solve that for x, I'm going to have 2 possible values, either that x is 0 or 4x minus 12 is 0, which means x would be 3. Now, there's a real subtlety in the language that someone has picked up on in the chat, and I also included it. I've got a page in the handout that says vocabulary break, and I've included the difference between a critical number or a critical value and a critical point. And there's a real subtle difference here. So I get the critical numbers from anywhere that my derivative is equal to 0 or undefined. So these are my two places where the derivative is equal to 0. But it's only a critical point if that point exists on the graph. So you just have to be careful about the domain of the function in terms of whether it's a critical point or it's a critical number. Back to this actual question. These are both critical numbers and critical points in this case, because the domain of my function is all real numbers. So if I need to find the absolute max and min, on the interval from 2 to 5, that says I'm going to come in here and I'm going to check. I've got to check the endpoints. And I need to check any critical number that's inside of that interval. And in this case, 0 is not inside of the interval, so I'm not even going to worry about it. I'm throwing it out. I'm only going to worry about the x equals 3. So I'm going to check at x equals 3. And checking means plugging it into the original function to see the y values. So I've got 2 cubed times 2 minus 4, 5 cubed times 5 minus 4, and 3 cubed times 3 minus 4. Okay, 5 cubed is 125. Yes, that's a nice number that I think you ought to have memorized. This will look like 125 times 1, or just 125. 3 cubed is 27. And 3 minus 4 is a -1, so that'll be -27. 2 minus 4 is -2. 2 cubed is 8. 8 times -2 is -16. So my absolute maximum value is 125, and my absolute minimum value is -27. This class, I am making this up. I don't want anyone to think that like this is a real model for elephant herd size in Tanzania. I'm making stuff up. So an ethnographer in Tanzania is studying the impact of habitat destruction on the average herd size for African elephants. She's come up with a model where E of H is equal to H times E to the 1 over H, where H represents the size of an average territory for a single herd in square kilometers, and E of H is the average number of elephants in a single herd. I'm making this up. What's the reasonable domain for H, and what are reasonable values for E? So I am mixing up the classes, but I think on one of Martinez's assignments, you were asked to, on one of the worksheets, you were asked to think about the functional domain or a reasonable domain of a function. And that just means if we have some context, does it make sense for some of these things to be 0? Does it make sense for some of these numbers to be negative? So if I'm thinking about H is the size of a territory in square kilometers. I'm going to argue that an elephant takes up more than 0 square feet, right? Or more than 0 square kilometers. So the domain for sure is, it's got to be something bigger than 0. Now, could it be infinite? Probably not. The reasonable end point for that domain, I suppose, would be all of the land mass of the continent of Africa. I don't know what that is. Like, I don't know what the square kilometers is. Should have looked that up. That would have been fun. But I would say that the domain for H is 0 to the size of the African continent. Now, in terms of values that are reasonable for E, E is the average number of elephants in a single herd. Since E is a number of elephants, it really has to take on whole numbers. And it can't be 0. but I suppose it could be 1. It would mean that was the end of the herd, right? Unless something intervened, but it could be 1. I don't know what the upper end is, but I suppose it could be very large. Now comes the fun part. The question is, what does the model predict is the minimum territory size? Well, anytime I'm trying to find a maximum or a minimum, I have to start by taking the derivative and setting it equal to 0. So regardless of whether you're doing maximum stuff in class yet, everyone ought to be able to find a way to take the derivative of this function. So I'm going to give everybody a minute to find the derivative of this. By the way, if having different letters throws you off, it's okay to rewrite this to say, I'm going to even write this to say like y equals x times e to the 1 over x. If that feels more comfortable for you, it's okay to rewrite it. But I'm going to give everybody a minute to just take that derivative. Just being super practical. If this were a test question and I really was running out of time, I would honestly go, okay, well, I know it's a product rule. I'm at least going to give myself the pieces that I need for the product rule. And if I don't know what else to do, maybe I can get some of those in there, because I know for the product rule, I get to leave part of it alone, and I get to leave part of it alone. Haven't even really had to do any calculus yet. Now it's time to sprinkle on the calculus. So what is the derivative of h? And now comes the fun part. I have e to some stuff. So if I'm taking the derivative of e to some stuff, that's an exponential. So I know that I get e to the stuff times, chain rule says I've got to multiply by the derivative of 1 over h. Now, maybe if you're not sure how to take the derivative of 1 over h, I'm at least going to write 1 over h prime. Cool. Maybe I got some partial credit, a little bit more partial credit for that. Or even if you're not sure what to do with this piece at all, at least putting a little prime there so that we know, hey, at least I got the product rule part, right? Okay, so if I'm going to take the derivative of 1 over h, this happens to be one that I just have memorized because it shows up a lot. Like 1 over x shows up a lot as a derivative. But if I wanted to do that, kind of, I might come off to the side and just think about, well, what if y was 1 over x? That's the same thing as saying x to the negative 1. And if I take that derivative, I'm going to end up with, I'm going to bring that exponent down. So I'd have negative 1 x to the negative 2. You can leave it alone at that point, but I kind of have it memorized in my head as negative 1 over x squared, because I think it's friendlier to look at. And if you can take some of the simpler ones and commit them to memory, like if you've got enough memory, hard storage memory in your brain at the moment, which you might not, but if you do, committing some of those smaller ones to memory just saves up a little bit more time to work on other parts. So now I'm going to take that and essentially stick it in right here, but I'm going to switch it around to be our nice variables. 1 times e to the 1 over h, I'm just going to write as e to the 1 over h. Plus, and then this part, I've got h, e to the 1 over h, and then times negative 1 over h squared. So if I just had to find the derivative, I could stop there. But my question asked us to find the minimum, which means we need to set that derivative equal to 0. If I set this equal to 0, and I've got two pieces that are separated by addition or subtraction, I'm kind of always thinking, what can I factor out? And both of these pieces have an e to the 1 over h. So if I pull e to the 1 over h out, here I'm left with a 1. And here, if the e to the 1 over h is gone, I've got h times negative 1 over h squared. So if I like smush that together, I'd have negative h over h squared. And one of those h's would cancel out. So I'd have e to the 1 over h. Still on the screen, okay? Yeah. I'd have e to the 1 over h, and then 1 minus 1 over h. We're all neatly factored at this point. So I'm ready to set each of my factors equal to 0. I'm going to do the easy one first. If 1 minus 1 over h is equal to 0, h has to be equal to 1. The second factor, I know that an exponential term by itself is never equal to 0, because we've always got that horizontal asymptote happening at 0. Since this can never be 0, that is my only critical point. Yeah. Yeah, so that's a good question. So how do you know when to use which type of rule? So first of all, I do see the students like mixing up when I should be thinking about exponentials and when I should be thinking about powers. So that really comes down to where is the variable. So if my variable is in the base and it's a number in the exponent, I'm using power rule. But if those are swapped so that I have a number as the base and the variable in the exponent, then we're using one of our two exponential rules for derivatives. If it's an e, we kind of just go straight into e to the derivative of e to the something is e to the something. If it's a different number, like if it was a 3 or an 8 in the base, then we've got to remember to multiply by the natural log of that value. In terms of recognizing product and quotient rule, I think that mostly comes with practice. But again, it's about identifying what thing is the variable and which things are actually numbers. Do that rewrite. And then I would get your quotient rule gone. As long as you were able to like factor something out from the top, then you can cancel something out. Yeah. So I'm gonna go ahead and round this one out here in terms of looking at quotient rule. And the reason I know it's quotient rule is that I've got division. I've got something on the top and something on the bottom. So when I take this derivative, getting myself some space. So the derivative of the top, my variable is in the base and I have a number in the exponent. So that by itself is going to be power rule. I'd have 1/2 x to the -1/2. Then I'm going to leave the bottom alone, subtract off, leaving the top alone, and then multiply by the derivative of the bottom. But the derivative of the bottom is just 1. Then my quotient rule says I'm going to take the denominator and square it. Now, if the only thing I had to do was take the derivative, I would absolutely stop there. There isn't anything super straightforward jumping out at us that we can simplify. I don't have an x plus 1 in both pieces, so I can't cancel out an x plus 1 right now. This is kind of all we got. If I need to set this equal to 0, though, we're going to have to do more algebra. Should we do the more algebra? Okay, I saw some head nods in the room. I'll go for that. So if I'm going to do more algebra, setting this equal to 0, if the denominator is 0, the whole thing is undefined. So I'm not worried about that. I'm really just worried about where is the numerator equal to 0. I could also think about this as whenever we have fractions, I can multiply both sides by the same thing to get rid of those fractions. And 0 times some stuff is 0. So on the top, I'm just going to rewrite this. I've got 1/2 x to the -1/2 times x plus 1 minus x to the +1/2. And that whole thing is equal to 0. Algebra wise, I have two things separated by addition or subtraction. So I'm hoping I can factor something out. They both have an x raised to a number. So I know I can factor out an x raised to the number, and I'm always going to choose the smaller of the exponents. So in this case, that's going to be the -1/2. Well, if I factor that out, the front piece isn't too bad because I pulled out the ugly part. So I'm left with 1/2 and then x plus 1. The back part is always the slightly weird one. I know that these exponents don't match, but the bases do. So I need something with the same base, and I need an exponent so that when I distribute this back in, I get back to our original thing. So I've got x to the -1/2 and x to the something, but I need these two exponents to give me back a +1/2. -1/2 plus 1 is what gives me a 1/2 back. So that's how it factors. So I've got x to the -1/2 and then inside 1/2 x plus 1/2 and then minus an x. If x to the -1/2 was equal to 0, we'd have a problem because that 0 would be in our denominator. So this can't be 0. Because it's in our denominator. And this other part, if I set it equal to 0, I can combine the negative x with the positive 1/2 x. And I'd have 1/2 minus 1/2 x is equal to 0, which would tell me that x would have to be 1. So in terms of finding, I think on this one, I asked us to find that absolute extrema on 0 to 4. This is our only value that we get from thinking about the relative extrema or the critical points. So to find the absolute extrema, I just need to check x equals 0, x equals 1, and x equals 4. I'm going to do these really quick in my head. Square root of 0 is 0, and 0 over 1 is still 0. Square root of 1 is 1, and that would look like 1/2. Square root of 4 is 2, and that would look like 2/5. So in terms of which one of those numbers is the smallest, 0 is the smallest. And then between 1/2 and 2/5, who's bigger? So there's my max.